This podcast is about solutions and the most common kind of reactions in solutions, which are precipitations, and something called net ionic equations, which we write for those reactions. So the first thing to think about is what happens when a solid, an ionic compound, dissolves in water. So, for example, if we have sodium chloride, which is a salt, which is a solid, like a white solid, and we put it into water, it dissolves pretty well. And the reason why this happens is that each ion comes apart, so the ionic compounds, the ionic bonds are broken, and then each ion, chloride, is surrounded by water, and sodium is surrounded by water. So each ion is more attracted to water than it is to its partner in its ionic compound. Notice that when it's solvated, when it's surrounded by water, the chloride ion is surrounded by the hydrogen side of water because that's the positive side of water, and the sodium ion is surrounded by the oxygen side of water, which is the negative side of water. So that does make sense. So some ionic compounds don't dissolve, and why is that? And that's because their ionic bonds that they form are stronger than their attractions to the water molecule. So they stay together and they stay solid in solution, and we say that they are insoluble. And we use solubility rules to figure out what compounds these are going to be. So talk a little bit about ratios. What happens, what do you write if you have 5 moles of calcium bromide, which is a salt, and you put it into water and it dissolves? How many moles of each ion are going to be in solution? So we need to look at the ratio here, and the first thing to do is to write the solvation equation. So calcium bromide, which is a solid, that's the S, gets put into water, and when it falls apart and it dissolves, it makes calcium ions, which calcium has a 2 plus. The AQ means surrounded by water. That's what we write. And then each bromide ion is totally separate from each other. So I get 2 bromide ions. Each of them are aqueous, or each of them are surrounded by water. So when we look at the ratio, if we had 5 moles to start with of calcium bromide, and everything went into water, we'd have 5 moles of calcium ion. So we could use that. We could use Avogadro's number to calculate the number of calcium ions if we wanted to. And then because the ratio is 2 to 1, we'd have 10 moles of bromide ions in solution, because there's 2 bromide ions for every 1 calcium bromide formula unit. So we talked about electrolytes earlier in the year, but it's worth repeating now. When you have pure water with nothing dissolved in it, that solution is not going to conduct electricity. So the light bulb is off here. Pure water, not conducting. If you had solid salt, like sodium chloride, and you put the electrodes in that, it also would not conduct, even though it's ionic. Because it is solid, the lattice structure isn't moving. The ions are not moving greatly, so they can't conduct electricity. However, when you combine them, you make a salt solution. Everything's dissolved. It looks like this. Because the ions are each surrounded by water individually, they can move around. And because the ions are moving, then it means it can conduct, electrons can move, and it can conduct electricity. So then the light bulb would come on. So predicting a precipitation reaction that's going to happen in solution, what happens during a precipitation reaction? 2 ions in solution find each other and form an ionic compound, an insoluble ionic compound. Why does it form? It forms because, again, they have a stronger attraction to each other than they would individually have for water, for being surrounded by water. And we're going to use solubility rules to predict which compounds are going to be insoluble and form solids in water. So here are again the solubility rules which we saw earlier in the year. The way these are organized are soluble ions are on the top. So those are anything in group 1, ammonium, nitrate, chlorate, acetate, most halogens, but there are some exceptions to the halogens, and then typically sulfate, but there are exceptions to the sulfate also. So what that means is that halogens are usually soluble unless they are with silver and lead, and that's how the sulfates work too. The bottom part of this chart is insoluble ions, so these are typically solid in solution or insoluble hydroxides, but then there are exceptions. Group 1 is always an exception, ammonium is always an exception to all of the typically insoluble ions. You don't have to memorize these, you have the chart, but you definitely have to know how to use it. So let's look at some a picture view of what's happening, and then we're going to write our own. So here in this reaction we have potassium chloride, which is AQ, which means it's dissolved in water. Everything, the ions are each surrounded by water. It looks like this. We've not drawn the water molecules here just to keep it easier to see, but potassium and the chloride come apart, and they're each solvated, they're separated from each other, and they're all dissolved in water. Silver nitrate, also aqueous. Again, all the ions come apart. Notice that the NO3 is the polyatomic anion, nitrate, and it makes one particle, NO3, but it sticks together. So we think of it as one thing, even though it has nitrogen and oxygen stuck together. And the nitrogen and oxygen do not come apart because as a group they are a particle, an anion. Notice that these look like clear solutions here, which makes sense because everything is dissolved in water. So when these are mixed together, what we are going to do here is imagine that we could take a picture before anything happened. Right after we mixed both solutions, all the ions are going to be in solution, and this is before any reaction has taken place. So we've got all 4 ions, the potassium and the silvers and the nitrates and the chlorides are all going to be mixed together. And then what happens? The silver and the chloride are going to find each other, and that's what's going to make a solid here. That makes the S. And in the picture, we draw that down somewhere down at the bottom. You want to show that they are bonded together. They're not free in solution anymore. They're stuck together, and that's what's going to make them a solid. And notice that the ratio has to be fixed. So in this case, the ratio is 1 silver for every 1 chloride. So make sure in your picture that you show that ratio. The potassium and the nitrate are still free in solution. They're not making a solid, they're not joined together. And when we write the formula, we write KNO3 with the AQ, but they're not really a compound, they're not really together because the potassium is separate from the nitrate in solution. Okay, so we are going to write this exactly the same thing. We're going to mix. The names in the boxes are correct. It's lithium carbonate and copper nitrate. This should say copper nitrate up here. So pay attention to the boxes. Each of them we're going to write what it looks like when it's in solution. 2 solutions, mix them together to make a combined solution, and then what happens, what does it look like after a reaction has happened. Okay, so the first box has the solution of lithium carbonate, and notice in this one that because the formula is 2 lithiums for every 1 carbonate, because lithium is +1, carbonate is -2, in my solution, my ratio, I have to have 2 lithiums for every 1 carbonate. So the ratio has to be consistent in your solution. So similarly, copper nitrate, which has the formula, copper 2 nitrate, which has the formula CuNO3 because the copper has a charge of +2. Remember that that's what the 2 means in copper 2 nitrate. Has a ratio of 1 copper to every 2 nitrates. So that has to hold true in the solution. So I've got 1 copper. In this case, I put 2 coppers in here, so I had to have 4 nitrate anions. Mix everything together. Imagine we had a super chemistry camera that allows us to take a picture before any reaction has taken place. These are all supposed to be, because of space, it's hard to fit everything in here, but these are all supposed to be spread out away from each other. All the ions are mixed together. The ratios are steady. Again, I have 1 copper for every 2 nitrates, and I've got 2 lithiums for every 1 carbonate. Mix everything together, and then you have to figure out which ions are going to get together and form a solid. In this case, copper and carbonate are going to find each other, and those two are going to be insoluble according to solubility rules, and they are going to make a solid. So drawing solids can be a little bit tricky. The important thing to remember is that in the solid, they are still ions. Carbonate still has a -2, copper still has a +2, but they are all touching each other. They are all joined together. They are not free in solution. That's one thing. And the ratio is still the same as the formula ratio. So in this case, because copper is +2, carbonate is -2, I'm going to have 1 copper for every 1 carbonate in my solid compound. So I've drawn these as sort of a lattice type structure to show that it's a solid. And then everything else is still in solution. The lithium is still floating around surrounded by water. Nitrate still surrounded by water. So when I write the reaction, lithium carbonate, aqueous solution, that's the first box, plus copper nitrate, aqueous solution, that's the second box. Mix them together, form a solid, copper carbonate. That makes the solid that I drew down here, the lattice structure. And then lithium nitrate is aqueous still. It is still in solution. So I write the ions for lithium and nitrate still in solution, surrounded by water. The ratio is still good. I still have 1 lithium for every nitrate because that's my formula here. 1 lithium for every 1 nitrate. But they're not really together. We draw them together as a way to keep track of all the atoms and all the ions and make a balanced equation. But the lithium and the nitrate are not really together. So on this next box, again, the formulas are correct, the ones in the box. So it's potassium hydroxide plus barium chloride. This should say barium chloride up here, not barium nitrate. Write the pictures in the box for the aqueous solutions. Show what it looks like when you mix them together. Show what it looks like after a precipitation reaction has happened and the solid has formed. And then write the balanced equation down at the bottom. And when you're done, turn it back on and check your work. Okay, so in this picture, like the one previous, the aqueous solutions have to have the right ratio, 1 potassium for every 1 hydroxide. Show that they are free in solution surrounded by water. Barium chloride, the ratio is 1 barium for every 2 chlorides. And then mix them together, and then what happens is the barium and the hydroxide ions find each other, and those make the solid. And then we draw the solid as a lattice structure, usually down at the bottom because it usually does sink. And notice that the ratio here is 1 barium for every 2 hydroxides in my barium hydroxide formula. You have to show that same ratio in the solid product. Sometimes this gets hard to draw. It's not as easy as 1 to 1, but you have to figure out a way to do it. They have to be touching each other. They have to be have the correct ratio to show that they are not free and surrounded by water. They are forming a structure. And then the chloride and the potassium ions are still floating, dissolved in solution. The balanced equation, we call this the molecular equation. Potassium hydroxide, barium chloride solutions mixed together make solid barium hydroxide. And then potassium chloride, again, we write the formula here, but they aren't really together. They're both free and dissolved in solution. So we're going to put all that together into something that we call a net ionic equation. The first thing that we write is the balanced equation that we usually are used to writing, and we call that the molecular equation. So silver nitrate, aqueous solution, mixed with sodium chloride, aqueous, and it makes sodium chloride solid, that's the insoluble solid, precipitate, and then sodium nitrate is the other product, but it is in aqueous solution. So we start with the molecular equation here at the top, and then what we do is everything that says aqueous, we're going to pull it all apart and show what it really looks like in solution. So all the aqueous compounds are really all by themselves surrounded by water. So we write this as, we call it the total ionic equation. So silver and nitrate are separated from each other. Sodium and chloride are separated. We mix them together, we make silver chloride solid, and sodium and nitrate are separated. And then notice that just like an algebra problem, we can cross out ions that appear on both sides of the equation. So nitrate is over here and on the right. Sodium is on the left and on the right, so we can cross them out because they cancel. We call them spectator ions. They don't do anything. They just sit around and watch everything happen. And we are allowed to get rid of them. They appear on both sides of the equation. And then you rewrite what is left over when you're done, and that is what we call the net ionic equation. So this is what's really happening in this reaction, even though the complete reaction looks like this. The net ionic equation for this reaction looks like this. So writing net ionic equations, the process is write the formulas, write the balanced equation, predict the states, figure out if everything is aqueous or solid. Everything that's aqueous we pull apart and write the total ionic equation for all the ions separately, cross out any spectators, and then write what's left over, and that's the net ionic equation. So try this on your own, and then the first one is done in the video, and the rest of them are, the key is on Schoology. Okay, so in this reaction, aqueous solutions of calcium chloride and potassium hydroxide are mixed together, and the molecular equation is has a 2 here to balance it for KOH. It makes solid calcium hydroxide, and then the other product is potassium chloride, which is aqueous. The total ionic equation, one thing I want you to be careful with is because there are 2 chlorides in calcium chloride, I need a 2 out front here. Both chlorides come apart, so I can't use a subscript 2. I have to use a coefficient for every single ion that comes apart. For potassium hydroxide, because of the 2 potassium hydroxides, it means I get 2 potassium, aqueous, and 2 hydroxides, aqueous. The product, calcium hydroxide, is a solid, and the other product is 2 potassiums and 2 chlorides left over. Cross out all the spectators, and what we have left is calcium plus 2 hydroxide ions gives us calcium hydroxide solid.